Hello and welcome to our next video. This is the last one for examples in topic 4. Just a reminder again, in case you haven't watched the other videos, I do encourage you to watch them in order. Topic 4 is broken up into 3 parts just to make it more manageable. This is the third part that I call 4.3, and part B, where we just work through some more examples. We've done one where we write everything by hand, and now we're going to do a very similar one, but show how we can use a spreadsheet software like Microsoft Excel to make things just a little bit more convenient. It's only a matter of convenience. To give you some options, choose which one or mix the two, whatever you prefer. Also a reminder that we will refer to problems in the statistics book. Very good introduction regardless of your discipline, but this one does focus a little more on psychology. Don't let that stop you from using this book. A very good introduction book. We're on page 173 today, number 18, that I'll move to the top here. We're not going to do all of it. We'll do number C, but let's read through it to see what it's all about in case you don't remember the previous question or you haven't done it. The previous video B1. For each of the following studies, the samples were given an experimental treatment and the researchers compared their results to the general population. For each, carry out a z-test using the 5 steps of hypothesis testing for a two-tailed test at a 1% level and make a drawing of the distributions involved. Also, let's find a 99% confidence interval. One thing at a time though. We're going to go give ourselves some time and slowly break down the steps in hypothesis testing. So we don't have to worry about all of it. We just want to do one step at a time. So first up, maybe let's write it over here. We want to write the two populations. Population 1 will be individuals that we're investigating under investigation, and population 2, Excel wants to autocorrect, not autocorrect, guess what I want, the general public, or whatever they said. I want to compare individuals I'm giving the special treatment to people in general. And then our null hypothesis will be, I don't want to worry about math symbols here, so I'm just going to write mu1 being equal to the general population mean of 10. If I look at my table here, we're doing C. Let's highlight that. Let's highlight that. 18C. If we look at C, they have, a population of 12. Excuse me. Let's update that to 12. And we also have a population standard deviation. We took a sample of 50 people for the experimental treatment, and we got a sample mean of 12. 12 as well. Oh, that's not what I want. It's going to be a little silly, but we're going to do C and D because the spreadsheet software is going to be so easy to recycle our layout and redo calculations, you'll see. So you might notice that, the sample mean is exactly the population mean. So what is that going to, what does that result in the hypothesis test conclusion? Well, let's see and be sure. And then we'll mix it up as well with D. So for now, let's focus on C. Let's not get ahead of myself and focus on one hypothesis step, hypothesis testing step, one step at a time. Alrighty, so let's also make a note of the research hypothesis, of course. Now they say It is a two-tailed test. So my hypothesis is null hypothesis. It's equal to the population 2 mean, or it is not. Now I don't want to mess with math symbols here, so I'll just say not equal to 12. All right. Then we're moving on. I'll just do it with spacing. Step 2 here will be my comparison distribution. Comparison distribution is the distribution, let's write it like this, distribution of means. So I'm trying to compare how does my sample mean sit in the distribution of all possible sample means. So I'll call that mu underscore m, and that is going to be my 12, the same as the distribution of individual scores. Sigma underscore m will be, let's move that down a little bit and write sigma over here, the population of individuals. That is given as 4 over there. So we'll put that as a 4. And sigma m is then going to be, oh, let's write my sample size as well. I want more things here. Sample size n is 50. We can double check in the question here, 50. So the standard deviation of the distribution of individual scores is connected to the standard deviation of the distribution of means by way of my formula here, formula 5-2, that states it in terms of variance, but I can easily convert that by taking the square root on both sides, and then the standard deviation sigma m is sigma divided by the square root of the sample size. So let's put that in as a formula. So we'll have sigma divided by square root. And you see here that Excel notices or guesses what you want. For simple functions, I don't have to use the insert function. Once I get used to them, capital doesn't matter. Square root of n, like so. So that gives us our standard deviation of the distribution of means. And if I calculate it as a formula referencing other cells, I've been bad with my coloring here, but that's okay. Then I can update it for a future question, and it becomes easier and easier instead of writing everything from scratch. Just an option for convenience if you want to. Now, I will highlight these. I know the sigma m was technically a calculation, excuse me, but just to highlight it so I can easily spot it later. Really doesn't matter what your color coding system is. So that was our second step in the hypothesis testing breakdown, where we just get all the information of the comparison distribution, in this case the distribution of means. Then next we want to calculate or determine our cutoff Z score. In this case, because it's a normal distribution, it would be a Z score using, we might not want to put it in text. We want to maybe have alpha as an input cell. So I'll use a separate cell here for alpha, 0.01, which is what the question is asking. Here, 0.01 level. So that's going to be our alpha. And now we have to find, let's draw it while we talk about this one. Now, in Excel, that's the one benefit of drawing things by hand. It looks better than just the rough drawing that I try to make symmetrical in Excel. It's not bad. I like it. It's a little off always, but that's okay. We want to, let me give myself a bottom line here, get some lines. Line over there, like so. And then we want to know, it's a two-tailed test. So if I split it up, let's say there, symmetrically on both sides, and same on the other side, then I want this little piece here to be half of alpha. So you can see this as 1% and then 0.5%. And over here, 0.5%. And then, of course, in the middle will be my 99%. Or you can do it as the decimal version. Because I'm going to use the cell in the calculation, I have it as a decimal, the decimal version of 1%. So keep that in mind. Don't get confused between the two. So I want to find the, let's call it Z cutoff. Let's do it like this, cutoff. So we have seen this before, but it's a more, I guess, complicated function, a bigger function. So maybe I don't remember. I'll search for normal. Maybe I haven't used it yet, so it doesn't show up in my list of recently used functions. I want the standard normal, the Z scores. So that's where this .s comes in. And I have two options. The norm.s.dist returns the standard normal distribution, the probability or percentages, given the Z-score. No, that's not what I want. I'm looking for the Z-score. The inverse function, given a probability or a percentage, returns the Z-score, returns the inverse of the standard normal. Okay, so that is the one that I want, and it's always going to be cumulative. So I can go one of two ways. I can look for this 0.5%, or I can go look for 99.5%, and then I'll get the positive version. I'll do that just to mix it up. I'll say here, what's the simplest way to do it? Now, in this case, we're not going to update the alpha to a different value, so you can put in here 99.5% if you want, because it's cumulative. I'm looking for this Z-score over here on the right. I like the positive one, but you could also, I think last time we just put in 0.5%, and then notice here the temporary answer, 2.575. If I put in 0.5%, I'll just get the negative version. So the symmetry can be exploited to whatever I want. Let's go with the positive one in this case. I can also use this alpha value. Let me demonstrate that and say this divided by 2, and you see you get the negative because that's the same percentage as the same probability, decimal version of the percentage of this one. So let's go with 99.5%, but you have a lot of options there. That's my positive Z cutoff. So of course this is going to be, I'll put it here in brackets, plus minus, because it's a two-tailed test, just to keep in mind for the future. So my Z cutoff is positive or negative. Alrighty, next up we want our observed score? Well, our observed sample mean is, they say in the question, 12. 12 over here. 12. We have to convert that to the Z observed Z score, by taking that, subtracting the comparison distribution mean, dividing by the comparison distribution standard deviation. Now, of course, it's 0 because 12 and 12 are the same. How do I get that? Oops, no, I want the formula sheet. It's not explicitly on our formula sheet, but 3-1 is a good reminder for how that works. 7-7 is as well, but that is a future topic, so I don't want you to get confused by looking ahead at formulas that aren't quite the same. So of course our Z observed is going to be 12, as I suspected. The sample mean that I get is exactly the distribution mean I'm testing against. So it's a little bit of a rare occurrence. Usually we don't get the comparison distribution population mean exactly. However, we'll update that to part D shortly. We'll get a conclusion. Conclusion is, when I compare the Z cutoff to the Z observed, we see that our Z observed score is right in the middle, not extreme at all. So we'll say here Z observed is, let's say, in between, we could say it like this, plus minus Z cutoff. And then we, oopsie, or did I write a random slash there? Just my finger slipping. We do not reject the null hypothesis. The evidence is not strong enough at all to suggest that mu1 is different from 12, the general population mean. Result inconclusive. You can write all of this, you could just write some of it. I'd like to be a little mathy here, a little specific, and then say it in more common words that the original question uses. All right. So they want an extra bit here, which is the confidence interval. Confidence interval. So here it is a little strange perhaps, but we'll go with it. When the sample mean is exactly the same as the population 2 mean, it's not quite what I expect or what I'm used to. I'm used to some variation, but still, we are constructing our interval. Let's go left and right. The interval we're constructing around this observed population mean in the same way here, but we're centering it at the sample mean, which in this case happens to be exactly the same as the population 2 mean. So our result for the confidence interval will look very similar. It won't usually. We're centering it around our sample mean because our sample mean is our best guess for what the true population 1 mean is. In this case, it doesn't seem to be different. It might still be a little different. We don't know. Our best guess is 12, and we give ourselves a little window, a little interval around this best guess because it's unlikely that we are spot on, and we won't know if we are. So we want to give ourselves a higher probability, 99%, casually speaking, of having an interval that does contain the true population mean, because we never know what it actually is. So our percentages are the same, and therefore we can reuse this 2.57583 Z cutoff value now as the distance, essentially, from the observed mean. So we're going to go this many standard deviations from M, and let's calculate that. We'll take our M. For the left one, we'll subtract the Z cutoff times the standard deviation. I'll show you that like so. And for the right side of the interval, I'll do it manually. We'll take the mean and we'll add this many standard deviation steps from the mean. So that will be our interval, where we are 99% confident that the true population mean is in that interval. All right, so let's see how the spreadsheet makes it a little bit more convenient if we now wanted to, actually I'm not going to overwrite this, I'm just going to copy this so we don't lose it completely. I'll just make a copy. And if we wanted to do part D, maybe. There, whoopsie, what is different? What is different? This one. That's what I'm looking for. Let's see. In D, our population mean is 14. Standard deviation is still 4. So the population mean is 14. I'll update that. And of course, that features in our hypothesis statement. We still have population 1, population 2. In the same way, our distribution of means, population mean is then 14. Sigma is still 4. Now we have 100 sample size, and you see our standard deviation of the distribution of means, our comparison distribution, updates accordingly because we had the formulas built in. So we didn't have to actually recalculate it. We just changed the input. Then we go to finding our cutoff Z score, same alpha, so that doesn't need updating, and our percentages, our visualization here of what's happening on the comparison distribution is the same, and therefore our Z cutoff score will be the same as well. But in this case, the observed mean is, oh, it's also 12. Okay, also 12, so that stays the same. And then we calculate our Z observed in the same way, but because we updated some of the things, that automatically gets updated as the sample mean minus the comparison distribution mean over the comparison distribution sigma. It's gonna get a little noisy because there's a truck outside. I apologize in advance. I'll try and wrap it up quickly. And we get a -5. So we're way out to the left beyond the negative Z cutoff line. So we can update this and say the Z observed is less than the negative Z cutoff. That is extreme, and we do reject the null hypothesis. The evidence is strong enough to suggest that, whoopsie, that my population 1 mean for those that got the treatment is different from 14. We got a 12 where the general population is 14. So that is different enough. I didn't know looking at 12 and 14, but based on everything else and the variance, it's actually very different. Confidence interval, let me check. It updates automatically. That's the beauty of it. I'm building it around 12 with this updated sigma. Same z-scores because my alpha was the same for my confidence interval. Let's write that maybe here. 99% confidence interval. Left and right. So I suspect, based on the evidence, that the sample mean, that the population 1 mean, those that have the treatment, is different from 14, and I suspect it falls in this range with 99% confidence between 10.9-ish and 13-ish. I don't know where it is, which is why I build an interval around my mean, because I don't know if it's 12 or not, and I don't know how close to 12. I can associate a level of confidence with my guess of where the true population mean sits, and if I decide on 99, that gives me a window. If I decide on 95 or 90 or something else, of course, then the window will be different to match that slightly lower confidence. Okay, so that wraps up our example, working through the steps of hypothesis testing in this basic introduction setting. We'll slowly add to it some variety in the situation, but the general logic and the general steps behind setting up and working through my hypothesis testing procedure will be the same. All right, until next time.